Previously on Physics for Engineers. In Unit 2, we see the effect of force in the state of motion of a body. Newton's first law explains how the object remains at rest, or how an object sustains its motion. In Newton's second law, we learned that, if a net external force acts on the object accelerates. We see clearly that force and motion are really interrelated. Usually we exert force on a body because we want it to move. We want the object to have displacement. We lift and push things. We go up and down the stairs. We do some workout to maintain our body physically fit. But have you ever asked yourself, why we get tired, thirsty and hungry after performing these activities? What we do after is that, we look for drinks and food because, we believe that, we need to regain our energy that has been lost while doing these physical work. In this unit, we are going to discuss another three important quantities in the field of physics: work, energy and power. We shall see and discover how these concepts are vital to your quest as future engineers. Good luck. Now let us begin our discussion with work. Work, denoted by letter W, is said to be done on an object, when it moves under the influence of a force. Work done by a constant force F, is given by the product of the force F, and the displacement, delta x, or delta y, moved in the direction of the force. Consider a toy train. It is being moved, along a horizontal surface, by applying a horizontal force exerted by the hand. This force causes the toy train to move with a displacement of delta x, hence this force performs work on the toy. For as long as the applied force causes motion on an object, that force is doing some work on that object. The SI unit of work is the joule, or J. 1 joule is the amount of work done by a 1 Newton force which causes a body to move 1 meter distance. In English system, the unit of work is in pound-feet, for as long as the units of force and displacement are in pound and foot, respectively. In CGS system, the unit of work is dyne centimeter. Take note that when applying this formula, make sure that the force and displacement are parallel to each other. If the force is applied perpendicularly to horizontal surface, obviously the box will not move, hence the work done by this force is zero. It is also important to note that the force F in the formula can be any type of force. It can be weight, normal force, tension, friction, and applied force. We will consider this idea on next slide. Now, let us try to investigate the work done by each force acting on a body, and the total work done. Imagine a toy train, that is pulled along a horizontal table, by means of a string, that makes an angle, theta, from the surface. The train has traveled with a displacement delta x. In order to determine the work done by each force acting on the toy, we draw its free body diagram. Here we see that there are 4 forces acting on the toy. Its weight, normal force, tension, and kinetic friction. These are the forces that acts on the toy as it travels along the table. We resolve tension in terms of its components, T sub x and T sub y. Now we're all set. Since we have 4 forces, we have also 4 works to be determined. Work done by the tension. Work done by kinetic friction. Work done by the weight. And work done by the normal force. And keep in mind the general formula for work, that is force times displacement. And that if you apply this formula, make sure that the force must be parallel to displacement. Okay, let us consider work done by the tension. We see that only the x component, T sub x, performs work on the toy, since it is parallel with the displacement. The y component, T sub y, do not perform work since it is perpendicular with the displacement. Hence, we consider only T sub x. So the work done by the tension is, T sub x multiplied by displacement, delta x. But the x component is also t cosine of the angle theta, so the final expression for the work done by the tension is t cosine of the angle multiplied by the displacement, delta x. As you see, this angle theta is the angle between the tension and the displacement. Take note also that the work done by the tension is a positive value, since both Tx and delta x are positive values. In other words, if the force and displacement have the same direction, work done by the force is positive. For the work done by the kinetic friction, the kinetic friction also performs work on the toy, since it is also parallel with the displacement. The work done by kinetic friction is negative of kinetic friction F sub k times displacement delta x. Take note, this is negative because Fk is towards negative x-axis. But kinetic friction is also mu sub k times normal force. Since Fk and delta x are opposite to each other, the work done by friction is a negative value. In fact, the work done by kinetic friction is always negative, since friction is always opposite to the direction of the displacement. For the work done by the weight and normal force, since the weight and normal force are both perpendicular with the displacement, the work done by these forces are zeros. Remember that no work is done when the direction of the applied force and the direction in which the object moves are perpendicular to each other. Work is also zero when the force causes no motion on the object, just like when we are pushing against a fixed wall, or carrying a barbell steadily. Although work is a function of two vectors, force and displacement, work is a scalar quantity. It has no direction. Its value may be a positive, negative or zero without direction. In order to determine the total work done by all the force acting on the body, we simply get the algebraic sum of the work done by each force. Considering these four works, the total work done on the train is equal to the work done by the tension, by the friction, by the weight and by the normal force. Surprisingly, if we get the net force, summation of F, from these individual forces, then multiplied by the displacement, delta x, we will get the same value as the total work done using this expression. Therefore the total work done is also the work done by the net force on the object, that is net force times displacement. Now, we see here that the total work is a function of net force. We learned, from Unit 2, that if the body is at rest or moving at constant velocity, the net force is zero. Hence, the total work is also zero, no matter how complicated the free body diagram may be. An employee may go to work on specified time, let's say from 8 o'clock in the morning, to 5 o'clock in the afternoon, that is a period of 8 hours. The performance of employees, in doing similar task, may be different. An employee can do the task or certain work faster than others. In physics, in order for the work to be done, time is needed. That is how we introduce a new physical quantity called power. Power, denoted by capital P, is defined as the rate of doing work done by the force. Mathematically it is expressed as power P equals work W, divided by time interval, delta T. The SI unit of power is watt. 1 watt is the rate of doing 1 joule of work in 1 second. To explain this formula, consider two workers, Juan and Pedro, doing the same job. They are going to push the crates 10 meters along a level ground. Assume that they exert same amount of horizontal force, equal to 100 newtons. Juan can do the job in 10 seconds, while Pedro finished the job within 5 seconds. We see here, that when we use the formula, work W, equals force multiplied by displacement, 100 times 10, they performed same amount of work of 1000 joules. On what aspect they differ? They differ on how fast they perform the task, or the rate of doing work. And this is what power is trying to describe. If we compute the power of the two workers using this formula, power is work over time interval. Juan has a power of 100 watts, while Pedro generates 200 watts. From these values, we can say that Pedro is twice as powerful as Juan. We can also say that Pedro works faster than Juan. We see in the above illustration that an average human can generate around 150 watts. This value is so small as compared to the engines that can drive different forms of vehicle. A typical car engine can produce 90,000 watts. An airplane has installed engine with an average power of 7 megawatts, that is equivalent to about 78 car engines. Cruise ships are being propelled by 18 megawatts engines, equivalent to 205 cars. The space shuttle for transporting humans and cargo to and from orbit around Earth, is driven by around 27,600 megawatts engine. Wow! That is equivalent to 306,000 cars. Another common unit of power is horsepower, or HP. Horsepower is a unit of power in the English system. It is used commonly for describing the rate at which an engine can perform mechanical work. 1 horsepower was originally defined as the amount of power required to lift 550 pounds by 1 foot high in 1 second. This value was established by Scottish engineer and inventor James Watt, with horses while hauling coal. When converted to watts, 1 horsepower is equivalent to 746 watts. So a 90,000 watt car engine is equivalent to 120 horsepower. Wow, that is 120 horses. Can you imagine that? Power can be also expressed in terms of average velocity. From the formula, power is work over time interval. But we know that work is force times displacement. So the expression becomes, power is force times displacement divided by time interval. Now observe carefully, we learned again from Unit 1, that the delta x over delta t, is also the average velocity of the body. Hence, power can be also expressed as P equals force F, multiplied by the average velocity. And from Unit 1, for a uniformly accelerated motion, average velocity is simply the average value between the initial and final velocities. Now, we're ready to solve sample problems. Problem number 1. A horizontal force of 30 newtons pushes a box, initially at rest, a distance of 2.8 meters along a frictionless surface. Find the work done on the box. If there is a frictional force of 10 newtons between the box and the floor, what will be the new work done on the box? Now let us analyze the problem. Again, we have a box that is lying on a frictionless surface. And there is a horizontal force of 30 newtons acts on the box. The box is initially at rest. So the initial velocity is 0. Since the surface is frictionless, obviously the box accelerates. And according to problem, it moves a distance or displacement of 2.80 meters. So we are going to determine the work done on the box for a frictionless surface. And another situation is that, if there is a frictional force of 10 newtons between the box and the floor, what will be the new work done on the box? The first thing we need to do, is to draw the free body diagram of the box, just like what we are doing in Unit 2, at the beginning of each problem. So this is the x and y axes. Remember, that the x-axis should always parallel to the surface where the box is lying. This is horizontal surface. Therefore, our x-axis is also horizontal. And the y-axis is kept perpendicular. This is the box. Then we should indicate the forces acting on the box. So we have downward weight, the perpendicular normal force, and the applied horizontal force of 30 newtons. We do not include friction, since the surface is frictionless. And this box moves to the right. Then try to observe. The only force that performs work on the box is the applied force F, since it is the only force that acts parallel to the distance or displacement. The works done by the weight and normal force are both 0, since these forces are perpendicular to the distance of the box. So the total work is just equal to the work done by the applied force F. From the basic formula of work: force times the displacement, delta x. Substituting the values: 30 newtons times 2.8 meters. So the total work done on the box is 84 joules. Any questions so far? This is simple, isn't it? Don't worry, the best is yet to come. For letter B. How about if there is already a friction of 10 newtons? We go back to our free body diagram to include the friction. So friction is to the left, since it opposes the motion of the box. Since friction is parallel to the displacement, therefore it performs work on the box. Now the total work done on the box are work done by the applied force plus the work done by the friction. Work done by the applied force F is F delta x. And the work done by the friction is negative of friction times delta x. Take note, this is negative since friction is towards negative x-axis. Be careful on this. So we can factor out delta x. So the equation becomes applied force minus friction multiplied by delta x. Substituting the values, we have 30 minus 10, then multiplied by 2.8. So the work done on the box is 56 joules. As you see, the work done on the box is decreased from 84 joules to 56 joules, that is, a decrease of 28 joules. And this is the effect of kinetic friction. If performs negative work on the object. Now it's your turn. Let me see what you have learned. Exercise number 1. A car is being pushed by a man, 19 meters along a horizontal road, by exerting a constant horizontal force of 210 newtons. Letter A, how much work does he do on the car? Letter B, if he can push the car in 20 seconds, how powerful is he? Express your answer in watts and horsepower. Use the conversion 1 horsepower equals 746 watts. Letter C, what is the average velocity of the car? Problem number 2. A farmer hitches his tractor to sled loaded with firewood, and pulls it a distance of 20 meters along a level ground. The total weight of the sled and load is 14,700 newtons. The tractor exerts a constant 6,000 newtons force, at an angle 36.9 degrees above the horizontal as shown. Letter A, find the work done by each force acting on the sled. Letter B, the total work done by all the forces. Assume a coefficient of friction to be 0.4. To begin with, let us draw the free body diagram of the sled. So we draw our x and y axes. We put here a sled. Then we indicate the forces acting on the sled. First, the downward weight. Then the upward normal force. The tension in rope that the tractor exerts. This tension allows the sled to slide to the right. And lastly, the sliding or kinetic friction, which is to the left. Then it is convenient to resolve this tension in terms of x and y components, T sub x and T sub y. So this is Tx, while this one is Ty. Take note of the directions of these components. Now, let us answer letter A. Here, we are required to determine the work done by each force. So let us investigate again our FBD. We see that we have 4 forces acting on the sled: the tension, the kinetic friction, the weight and the normal force. Therefore, we are going to solve for the work done by these 4 forces individually. So let us begin with the work done by the tension. Since we express tension in terms of x and y components, we will determine which components performs work on the sled. Which one do you think? Is it Tx? Well, that's correct. Very good. Only the x component of tension performs work since it is parallel to the movement of the sled. The work done by the y component is 0, since it is perpendicular to the displacement of the sled. So the work done by the tension is T sub x multiplied by the distance, delta x. But Tx is also T cosine of the angle, theta. We substitute the values, so tension is 6,000 newtons, cosine of the angle, 36.9 degrees, multiplied by the distance, 20 meters. So the work done by the tension is positive 95,962.2 joules. This is positive since Tx is along with the direction of the movement of the sled. Now, next is the work done by the friction. Since friction is parallel to the movement of the sled, it also performs work. The work done by the friction is expressed as negative of kinetic friction multiplied by the displacement, delta x. This is negative since friction is toward negative x-axis. But friction is also mu sub k times normal force. Now, the problem is, we do not know yet the normal force. So, for the meantime, we label this as our equation 1. Now, what should we do to solve this normal force? Anyone? Very good, we consider the summation of forces along y-axis equals 0, since there is no motion along y-axis. From free body diagram, the forces along y-axis are T sub y, normal force, and negative of weight, equals 0. We can express T sub y as T sine of the angle, theta. Then we solve for normal force. We transpose weight and the T sine of theta to other side of the equation. So normal force is weight minus T sine theta. Substituting values. The weight is 14,700 newtons minus the tension, 6,000 sine of 36.9 degrees. So the value of normal force is 11,097.5 newtons. As expected, normal force is less than the weight of the sled and firewood. Now we go back to equation 1. We substitute the values. Negative of mu sub k, 0.4 times normal force, 11,097.5, and multiplied by displacement, delta x, 20 meters. So the work done by the friction is negative 88,780 joules. Again, we see that the work done by the kinetic friction is negative, since the direction of friction is opposite to the displacement of the sled. For the work done by the weight and the normal force. Since weight and normal force are both perpendicular to the displacement, delta x, therefore, the work done by these two forces are both 0. For letter C, now that we have solved the work done by each force, we simply add them all, to determine the total work done on the sled. So the total work is 7,182.2 joules. Try to observe the value between the total work and the work done by the tension. It seems that the total work of 7,182.2 joules is really less than the work done by the tension of 95,962.2 joules. This big difference is simply because of the work done by the friction. We can estimate the mechanical efficiency of the tractor by dividing the useful work, that is the total work, divided by the input work, that is the work done by the tension. So the estimated efficiency of the tractor is 7.5%. This is pretty low. But if we could somehow reduce the friction, the useful work may increase, so as with the mechanical efficiency. This is also the reason why heat engine should have good lubrication system in order to increase its efficiency in doing mechanical work. Again, it's your turn to showcase what you have learned. Exercise number 2. A 2.27 kg sack of flour is lifted vertically, at a constant speed of 4.0 meters per second, through a height of 12.0 meters. Letter A, how great a force is required to lift the sack? Letter B, how much work is done on the sack by the lifting force? Letter C, how much is done by the gravity? Letter D, What is the total work done on the sack? Congratulations for answering exercise number 2. Now let us consider an object that moves along an inclined plane. Problem number 3. A 100-gram ball rolls down a rough, 30-degree inclined plane of length 1 meter. How much work is done by the gravitational force on the ball? Now, let us analyze the problem. So this is the ball of mass 100 grams. And this is the inclined plane, which has an angle of 30 degrees, and length of 1 meter. So we are asked to solve the work done by gravitational force. And when we say gravitational force, it is actually the weight of the ball. So we are going to solve for the work done by the weight. Here, we do not need to draw fully the free body diagram, since what we are looking for is only the work done by the weight. So we only indicate the downward weight. Instead of choosing the length of the inclined plane as the displacement, we rather choose this vertical displacement, delta y, since we know that, in computing work done, the force must be parallel to the displacement. So here the force applied, which is the weight, is now parallel to this displacement, delta y. Although the actual path is 1 meter, don't be confused, we are going to use this vertical displacement, delta y, since it is the one that is parallel to the weight. So work done by the weight is negative of weight multiplied by delta y. This is negative since weight is towards negative y-axis. But what is delta y? Can anyone tell? Very good. Using your knowledge in solution to right triangle, delta y is negative of L sine of the angle, theta. Don't forget the sign negative, since ball's motion is downward. And weight is also m times g. So substituting given information. Mass is 0.1 kilogram, g is 9.8 meter per second squared, multiplied by negative of 1 meter, sine of 30 degrees. So the work done by the weight is positive 0.49 joules. Our answer is a positive since weight and displacement have the same direction. Are you still there? So let's keep up. Kindly answer, exercise number 3. A boy has a weight of 500 newtons, and can run up a flight of stairs in 10 seconds. There are 30 steps and each of them is height 16 centimeters. Calculate the boy's power. Assume that the boy's speed remains constant as he run on the stairs. Good luck. Hello everyone. Have you answered exercise number 3 correctly? I hope so. In this problem, we are going to revisit the problem we solved in Unit 2 about elevator. Problem number 4. From rest, an elevator in shopping mall can raise a maximum of 20 people, through a height of 10 meters in 8 seconds. The elevator and its passengers have a total mass of 1,600 kilograms. What is the power of the lift motor? Express your answer in horsepower. So let us begin. Imagine this is the elevator, that carries 20 people. According to problem, it is initially at rest, so V sub I is 0. The cable attached to the motor, allows the elevator to be lifted, 10 meters in 8 seconds. We establish the given information. So the initial velocity is 0. The displacement of the elevator, delta y, is positive 10 meters. The combined mass is 1,600 kilograms. And the time interval to reach this 10-meter height is 8 seconds. Now we are asked to determine the power of the motor, P, attached to the cable, which drives the elevator car. Now let us think carefully. The motor of the elevator system is usually installed at the top of a building. The power of the motor can be determined from the work done by the tension on the elevator car, since the tension is being developed by the rotating shaft of the motor. So before we solve for the power of the motor, we better start solving the tension first. Let us draw the free body diagram of elevator. we draw our axis. And this is the elevator. We have downward weight, W, and upward tension, T. We know that the elevator accelerates, because it starts from rest. Now, let us solve for the tension. We take the summation of forces along y-axis, by applying Newton's second law, since the elevator is accelerating. So this is equal to mass times acceleration. From our FBD, forces along y are tension, T minus weight, equals m times a. This is negative since weight is toward negative y-axis. But weight is also mg. Solving for tension, we transpose negative mg to other side, and factoring mass m. So tension is mass times the quantity a plus g. We do not have the value of acceleration, so we label this as our equation 1. We will go back to Unit 1, kinematics, by assuming that the elevator moves with constant acceleration. So delta y is equal to v sub I times t, plus 1/2 of a, t squared. Since v sub I is 0, we can cancel out this, to make the equation short. Then a little algebra, we solve for acceleration, a. Acceleration is 2 multiplied by delta y, over t squared. Then we substitute this expression to equation 1. So tension is, m times the quantity, 2 delta y over t squared, plus g. Alright, we plug in all given information. Mass is 1,600 newtons, delta y is 10 meters, time is 8 seconds, then you square it, plus 9.8 meter per second squared. The tension in the cable is 16,180 newtons. Now we're ready to solve for the power of motor. From the basic formula of power, that is work over time interval. This work is the work done by the tension, T multiplied by displacement, delta y. Over time interval 8 seconds. Pressing on the calculator will give 20.225 watts. Finally, we convert this to horsepower. So we multiply this by 1 horsepower over 746 watts. The power of the motor is 27.1 horsepower. So this is the power requirement of this elevator system. In real situation, we should round up this to, let's say, 28 horsepower. This problem is actually the preliminaries in designing elevator system mechanical engineers should know. Maybe someday, you're the one who will lead a project for elevator system of a high-rising building, that was designed by civil engineers. Of course, in order to run elevators, a good electrical system design is needed. And that will be the role of electrical engineers. Wow, really engineers work hand in hand.